This is a video lesson for solving free-fall motion problems. The learning target for this lesson is, I am learning to solve free-fall problems using a variety of strategies. Success criteria for this lesson are, I can solve real-world problems involving free-fall, and I can solve AP-style questions involving free-fall. So let's look at free-fall motion a little bit in review. So an object in free fall motion experiences only one force, the force of gravity. So if we ignore drag, gravity accelerates all objects at the same rate, which we call g. On Earth, g is 9.81 meters per second squared, which we approximate to 10 meters per second squared. At an object's maximum height, its velocity, v sub y, is equal to 0 meters per second. So again, when an object reaches that maximum height, as high as it can possibly go in the vertical direction, its vertical velocity is 0 meters per second. Free fall is symmetric, going up and down. So when an object is moving in a vertical direction, if it's going up, and then when it's coming back down again, at the same point in that trajectory, at the same point in the positive motion upwards, and in the negative motion downwards, it's symmetric. And then our kinematics equations in the y direction are y equals y naught, so the vertical displacement, plus vy naught times t, plus 1/2 at squared. V sub y squared is equal to vy naught squared, plus 2a times y minus y naught. So that's the final velocity squared in the y dimension is equal to our initial velocity in the y dimension squared, plus 2 times a times y minus y naught. So that's our displacement in the y direction. And then vy is equal to v naught y plus at squared. So that is our final velocity in the y direction is equal to our initial velocity in the y direction plus acceleration times time. All right, let's start with problem number 1. So this is not an AP question. This is just a regular free fall problem question. So an archer stands on a 15-meter tall wall and fires an arrow upward with an upward velocity of 30 meters per second from that height. What is the arrow's maximum height above the ground, and how long does it take to hit the ground? Okay, so we can draw a little diagram here. So we have a maximum, so we have a height of 15 meters. So we say that y naught is equal to 15 meters. Archer fires an arrow. So a little arrow here. It goes up, reaches this maximum height, and then it comes back down again. So we want to know what is the maximum height here. So what is this height? So this is y max. What is y max? And then what's the time that it takes to get to the ground? So time total equals question mark. Okay, so we're going to solve this problem a couple of different ways. So the first thing to note is that the velocity at y max is 0 meters per second. So anything at its highest point is going to, the velocity at any projectile's highest point, or any object that's rising and then falling again, its velocity is going to be 0. So our y naught, as I said here in the diagram, is 15 meters per second, or is 15 meters, and our vy naught, our initial velocity, is 30 meters per second. Okay, so we don't have time information yet, so we're going to use the kinematics equation vy squared equals vy naught squared plus 2a times y minus y naught. And our acceleration here is equal to minus g. Okay, so plugging in the information that we have, so our vy naught, our vy is 0. So we have 0 meters per second, and that's squared. Then we have 30 meters per second, that's squared, minus 2 times 10 meters per second squared times y. That's what we're looking for, the maximum height. So we'll call that y max minus, and we start at 15 meters. Okay, so we have 30 squared is 900 meters squared per second squared. Then we have minus 20 meters per second squared times y max, plus then we have 300 meters squared per second squared. Okay, so and that's all equal to 0. So I'm going to go ahead and simplify. I'm going to move the negative 20 meters per second squared times y max over to the left side and combine my like terms on the right side. So we have 20 meters per second squared times y max is equal to 1200 meters squared per second squared on the right. Divide both sides by 20 meters per second squared. So y max is equal to 60 meters. Okay, so the height at the maximum is 60 meters. Okay, so now we're going to do this. We're going to figure out the maximum velocity from this point, from the highest point down to the ground. So what is the max velocity when the arrow hits the ground here? So we're going to do this in 2 parts, and then we're going to figure out the time it takes. So I'm going to do some erasing, and then we will come back. Okay, so we've got our maximum height. So if we're talking about from this point to this point, our maximum height now becomes our y naught. So our y naught now is 60 meters, and we are looking for a y of 0 meters. And we're looking for Vy. We don't know our final velocity. Our initial velocity, Vy naught, is going to be 0 meters per second, because we're talking about our velocity at the maximum height as being, so the velocity at this point, this is Vy naught, so that's 0 meters per second. And we're going to use the same equation we used last time. Vy squared equals Vy naught squared plus 2a times y minus y naught. Okay, so Vy squared, which we don't know, is equal to 0 minus, because remember our g is negative, so minus 2 times 10 meters per second squared times y is 0 minus 60 meters. Okay, so we have Vy squared is equal to minus 20 times minus 60, which is equal to 100 and so that's what, 1200 meters squared per second squared, which gives us a final velocity in the y direction of 34.6 meters per second. And this is going to be a negative 34.6 meters per second because the velocity is going down. So it's negative 34.6 meters per second. Okay, so now we have our maximum height. So our y max is 60 meters. And now we need to know how long does it take. So how long does it take? Okay, so we're going to use Vy is equal to Vy naught plus AT to figure out how long it takes to hit the ground. So we have Vy is minus 34.6 meters per second. That's equal to our initial speed, which was 30 meters per second, minus 10 meters per second squared times t. Sorry, things are a little crowded here. So let's separate that right there. Okay. So subtract 30 from both sides. So we have minus 64.6 meters per second is equal to minus 10 meters per second squared times t. So t then is equal to 6.46 seconds. Okay, so our max height is 60 meters. Our time is 6.46 seconds. And that is how you solve this problem. That's one way to solve it. And the next slide, we'll look at another way to solve it. Okay, so we solved this problem one way with our kinematics equations. This way, now we're going to solve it using kinematics equations and the quadratic formula. So first, let's write out the quadratic formula. So we have minus b plus minus the square root of b squared minus 4ac, and all of that is over 2a. Okay, so we're going to use our y equals y naught plus v y naught t plus 1/2 a t squared equation, because this is the one kinematics equation that we have that is quadratic. Okay, if we plug our known information into this equation, we have 15 meters, that's our y naught. We have our initial velocity, that's 30 meters per second. And then we have, of course, our initial acceleration. So we have y is 0. Y naught is equal to 15 meters. Vy naught is equal to 30 meters per second. Acceleration is equal to minus g, which is minus 10 meters per second squared. And we're looking for t. We're actually looking for, we want y max as well. Okay, so let's plug everything in here. So y is equal to 0 equals 15 meters plus 30 meters per second times t minus 1/2 times 10 meters per second squared times t squared. Okay, so simplifying that a little bit, we have 0 is equal to 15 meters plus 30 meters per second times t minus 5 meters per second squared times t squared. Now notice that this is all these numbers are divisible by -5. So we can say we have 0 equals -3m minus 6 meters per second times t plus 1 meter per second squared times t squared. Okay, so this is our A, this is our B, and this is our C, if we're plugging this into the quadratic formula. Okay, so we have negative B, so that is 6 plus minus, so B squared is -6 squared minus 4 times A, which is 1, times C, which is -3, all divided by 2 times 1. Okay, so I'm just going to plug this into my calculator and we'll come up with our two answers. Okay, so we have t, because that's our variable, t is equal to, so if you plug in the positive and negative options here, so you have 6 plus and then 6 minus. For 6 plus, we get 6.46 seconds, and we get minus 0.46 seconds. So obviously, the one that we know is correct from the first time we worked the problem is 6.46 seconds. And of course, negative 0.46 seconds is not a reasonable answer for a time. So we can obviously choose 6.46 seconds. Okay, so this gives us how long it takes to hit the ground. So it does not solve for us the problem of the maximum height. So to find the maximum height, we still have to do the method that we used prior. We can't use this equation. We can't use this equation to find the max height. So we'll still have to use the previous solution to find the maximum height. But this is a way to find the time in one step. All right. Okay, example number 2. Observing a spacecraft land on a distant asteroid, scientists notice that the craft is falling at a rate of 5 meters per second. When it is 100 meters closer to the surface of the asteroid, the craft reports a velocity of 8 meters per second. According to their data, what is the approximate gravitational acceleration on this asteroid? Okay, so we are looking for g. So what is g? Okay, so we are given initial velocity, Vy naught is 5 meters per second. We're given final velocity, so Vy is equal to 8 meters per second. And we're given y naught, we could say is 0 meters, and y is 100 meters. So we don't have time. We don't know how long it takes, but we are given all of this information, and we're looking for g. So we can use the equation Vy squared is equal to Vy naught squared plus 2a times y minus y naught. So we'll plug all this information in and see if we can figure out. So in this case, our a is going to be g. So we have Vy squared, that is our 8 meters per second. We'll square that. It's equal to Vy naught, that is 5 meters per second. We'll square that. So plus 2 times g, which we don't know. Our final position is 100 meters further along minus 0 meters. Okay, so we could say that the that down is negative, so that would make this be negative 100 meters, so that would give us a negative g. So we have 64 meters squared per second squared is equal to 25 meters squared per second squared minus 200 meters times g. So move the 25 meters squared per second squared over to the left side, which gives us 39 meters squared per second squared is equal to minus 200 meters times g. Divide both sides by 200 meters, and we end up with g is equal to minus 0.195 meters per second squared. So it's a very small acceleration due to gravity, but it makes sense when you think about that the craft has fallen 100 meters and it's only gained 3 meters per second of acceleration or of velocity. Okay, example number 3. So we have 2 identical bowling balls, A and B, are each dropped from rest at the top of a tall tower as shown in the diagram below. So we have 2 balls dropped from the tower. Ball A dropped 1 second before ball B is dropped, but both balls fall for some time before ball A strikes the ground. Air resistance can be considered negligible, so we're not looking at air resistance. After ball B is dropped, but before ball A strikes the ground, which of the following is true? The distance between the two balls decreases, that's A. The velocity of ball A increases with respect to ball B. The velocity of ball A decreases with respect to ball B, and then the distance between the two balls increases. So the velocity of both balls is going to increase at the same rate. So if we look at the equation governing velocity, we could say Vy is equal to Vy naught plus AT, or if we think about it in terms of free fall, minus GT. So the time is singular. It's only times 1. So every second, the velocity is only increasing by a factor of 1. So if we created a table, we could see that velocity was only increasing by so each second the velocity of ball B is increasing at the same rate that the velocity of ball A was increasing. So if ball B is dropped a second after ball A, ball B is increasing its velocity at 1 second behind ball B, but it's the same rate. So the velocities are increasing at the same rate of minus g. The distance, however, is governed by this square here. So time squared. So the distance between the two balls is going to increase because every second the distance change between ball A and ball B gets bigger by this square. So after 1 second, ball A is at minus 5 meters and ball B is at 0 meters. The next second, ball A is at minus 20 meters and ball B is at minus 5 meters. The next second, ball A is at minus 45 meters and ball B is at minus 20 meters, and so on and so forth. So you can see that that distance is increasing as they fall. So the correct answer here is D. Okay, so what did we learn in this video? So we looked at solving real-world problems. So we need to read the problem, see what information is given and what they are looking for in the problem to solve it successfully. So what about AP style questions? Again, we're going to read the problem carefully, determine exactly what the question is asking for, and then make sure we're using the right equation. All right, thanks everybody.